Hi, I'm Kalyan. Today I'll be presenting our IROS 2021 work on joint sampling and trajectory optimization over graphs for online motion plan. This work is done in collaboration with my colleague Mustafa Mukadam. In this work, we look at the problem of online motion planning for robot agents in large, dense, highly dynamic and unpredictable environments. One such scenario is shown here, where the robot objective is to navigate to the goal while avoiding external obstacles in the environment whose motion is unknown. While doing so, the robot has to reason about all the multiple paths to the goal and pick the best one. Here, all possible paths are shown in red. Traditionally, the problem of motion planning can be classified into either search and sampling based planning or trajectory optimization approaches. Search and sampling based planning techniques are often considered complete with the ability to produce globally optimal solutions, also while handling the tightest of the constraints. However, they are also very slow and suffer from cuts of dimensionality, making them ineffective candidates for online motion planning. And on the other hand, trajectory optimization techniques are considered to be fast and can scale well for higher dimensions. However, they again suffer from a complementary set of problems like getting stuck in local minimas and failing to switch across different homotopies. What we need is a solution that combines the best of planning and optimization approaches to mitigate their individual pitfalls. Taking a step back to understand the complexity of problem we have on our hands, let's take the simple example of navigating to the designated red cross while avoiding the cat in motion. Here, the robot can either go to the right of the cat or to its left. What this means is that there exist two groups of solution belonging to two different homotopies. For instance, the paths on the right belong to the same homotopy because they are on the same side of the cat, whereas the path to the left is considered to belong to different homotopy, as it would have to cross over the cat to reach the paths on the right. What we want is a planner that can produce robust solutions by reasoning about multiple such homotopies, while having the ability to dynamically switch between them as time progresses and the environment evolves. Switching across to a different homotopy is particularly difficult for trajectory optimization approaches due to its run-ins with local minima. Few trajectory optimization works try to reason about local minima associated with homotopies by accounting multiple homotopies through better and multi-hypothesis initializations. GPMP graph is one such work that performs trajectory optimization over multiple interconnected initializations using factor graphs. A follow-up work extended this to dynamic environments, but both of these works were still limited to an offline setting and a fixed horizon setting that won't scale well for large environments or highly dynamic environments. In our work, JIST, we extend these prior approaches to online and receding horizon setting through integration of sampling-based planners. We now introduce our approach JIST. It is a unified approach that leverages the complementary strengths of sampling and optimization approaches and interleaves them both in a manner that is well suited for challenging problems of online motion planning in dynamic environments. We now explain JIST using an example of 2D navigation. In JIST, at any given time, we have the path traversed so far by the robot and the graph built so far from previous iterations. We then grow this graph using a sampling-based planner until the graph reaches a preset node budget. Post that, we optimize the graph using GPMP2 factor graph-based trajectory optimization technique. We then execute the optimal action determined by the new optimized graph. After that, we prune the graph to remove any unreachable nodes on it. While doing so, we also update our environment representation based on the latest sensor observations. This process is then simply repeated until we reach the goal. Since our approach combines both sampling-based planning and trajectory optimization, the obvious baselines we considered for our approach come from these individual categories. We consider an RRT star variant designed for dynamic environments as our sampling baseline, and a GPMP2 single chain variant designed for online dynamic environments as our optimization baseline. We now present various synthetic and realistically simulated environmental experiment results for our approach and the suggested baselines. The first experiment we consider is 2D XY yaw navigation in a 2D dynamic random forest. Here, in all our experiments, the robot is operating under limited visibility marked by the sign distance field gradient and also has noisy sensing and noisy action execution. As it can be observed, while the sampling optimization approaches fail to reach the goal, our approach just has no trouble doing so. Here, sampling and optimization approaches terminate in collision, while JIST successfully navigates to the goal. Similar to 2D random forest, another 2D navigation experiment we considered is narrow passage navigation while avoiding dynamic obstacles. Here again, while sampling and trajectory optimization based approaches terminate in collision, JIST successfully manages to navigate to the designated goal with ease. Another environment we consider is a realistic simulation in Gazebo, where an omnidirectional robot has to navigate to the goal while avoiding the realistically simulated pedestrians, all while performing its own sensing and execution. Here again, JIST does a good job of navigating to the goal successfully while avoiding the pedestrians. Finally, another domain where we demonstrate JIST's capabilities is manipulation. Here, using JIST, a sixth of simulated robot arm successfully manipulates its end effector to the goal while avoiding randomly moving dynamic 3D obstacles with ease. We now go over some quantitative results. In all our earlier introduced environments and domains, we perform multiple experiments under different initial settings and present aggregated results in this table. The metrics we look at are the success rate of reaching goal without timing out or terminating in collisions, the execution time taken by the robot, the computation budget for each method, and the normalized distance to the goal traversed by each robot. As observed in this table, on all these metrics, JIST outperforms its counterparts. We believe this is because of JIST's ability to reason about multiple hypotheses well and easily switch between them. For more observations and detailed analysis of results, please check out our full-length paper. To conclude, thank you for attending my presentation. Please check out our project page for additional details.